Let's do a few practice problems. That's the normal line between air and glass. We always measure the angle from the normal line. Which way do you think this ray is going to bend? Toward or away from the normal? Imagine the light ray going straight through. Is it going to bend away from the normal or toward the normal? You have to think about the waves striking the surface. This is the slow medium, that's the fast. So if it's going to hit here first, it's going to slow down, and then that side's going fast and bend this way. We say it bends toward the normal. Let's say we observe the experiment and we see the light ray has refracted to 35 degrees measured from the normal. Could you tell me what the index of refraction is for this glass? Using Snell's law, we have sine of the angle incidence on the fast side over the sine refracted, that's on the slow side, and we get 1.51. What are the units for this? Well, there aren't any. There's no units here, there's no units here. Could you calculate the velocity of light in the glass? Well, remember that refraction is based on the difference in the speeds of light in the medium. Well, we have a vacuum up here, that's 3 times 10 to the 8th meters per second. And now we can find the velocity of light in the glass because we know the index of refraction. It's simply this ratio. And we get 1.99 times 10 to the 8th meters per second. Yeah, it does work out that way. It is slower down in the glass. Same glass, now trace the ray. What's it going to do? Look at the waves coming up. That side's going to come out first. It's going to speed up and turn away from the normal. Our goal now is to find that angle. Snell's law was derived for going from fast to slow. So even though the incident angle is 40 degrees, it's on the slow side, you have to pretend the ray is going the other way. Put that angle down here. This is why I like to think of Snell's law as fast angle over the slow angle. Plugging in the data, we get a much larger angle than 40 degrees. Yeah, that makes sense. It bent away from the normal. The index of refraction is still the same. I haven't changed the medium. It's still the same glass. Well, what's going to happen if we try an angle of 60 degrees? We swivel the light over this far. Will it be able to come out? If you set up Snell's law and you try to find the angle, you're going to get an error. How come? Because the biggest the angle could ever be up here is 90 degrees. If that happens, you're beyond the critical angle. The light can't come out, it's going to reflect. It's total internal reflection. So why the word total here? Well, that's because when you are at a lower angle than this, below the critical angle, the light will escape, but there might be some that will reflect. If you look closely, you'll see some reflecting and some transmitting. But if you're beyond the critical angle, you'll get no transmission at all, and you will get total internal reflection. So how do we find the critical angle? That's the biggest angle we can have in the glass and still allow the light to come out. Well, what's the biggest angle you could have up here? 90 degrees. Well, that's on the fast side. So what's the sine of 90? It's 1, and that makes this the critical angle. We get 41.5 degrees. Let's see how that works when we trace this ray. We still have the same glass, n equals 1.51, and we have an incident angle of 70 degrees. Can we trace this ray? The refracted angle turns out to be 38.5 degrees. Now we have to see what happens at this interface. Well, that means I need to know the angle measured from this normal. How did I get 51.5? Well, if that's 38.5, then that's 51.5, that's 90, that's 38.5. Hey, it's 51.5. This isn't physics, it's just geometry. Will this ray escape? Well, if you do sine fast, that's this side, divided by sine on the slow side, equals 1.51, up, you get your error again. Of course, that's beyond the critical angle. When it reflects, these angles are equal. Now we can go find out what's happening over here. Well, we've got the same angles over here, 90 degrees. We're going to have 38.5 over here. So now if I go to do Snell's law again to come out, the 38.5 is on the slow side. I can go calculate the fast side. Well, yeah, it's going to be 70 degrees. It's the same numbers that we had over here. Now, this means that glass can act like a mirror even if there's no mirrored coating over here. You can see what I mean if I use a 45, 45, 90-degree prism of the same glass. And now we're going to let the light come in right along the normal line. Where will it go? It's going straight in. Both sides of the waves slow down at the same time so they don't bend. Now, what's the angle measured from the normal along the diagonal side? That's also 45 degrees. And it's not coming out because that's bigger than the critical angle. So it reflects at 45 degrees, which puts it on a path to come straight out. So this side acts like a mirror, even though there's no coating here. Let's see how that works with a real prism. Now, it's not 90, 45, 45. It's an equilateral, but same idea. So now take a look. Oh, I can see myself. Can you see my image over here? Well, how's that happening? The light's coming in over here, striking over here and reflecting and coming out there to you. There's no mirror here, it's clear. These types of prisms are used in periscopes, binoculars, telescopes to redirect the light without any distortion from a mirrored coating. Well, let's see if you can trace the ray through this prism. 70 degrees and 70 degrees, and it's 65 degrees from this normal. The index of refraction for the glass is still 1.51. Why don't you pause the video and try this on your own before I work it out? Okay, here we go. Setting this up, we get 36.9 degrees. It strikes this side. We draw on the normal line. We need that angle to figure out what's going to happen now. How do we get that angle? Well, look, we have a triangle up here. That's got to be 53.1 degrees. If these two are 70, that's 40 degrees. Now we can figure out what that is. There's got to be 180 degrees in a triangle. So we got 86.9 degrees. Now we can get that. We have 3.1 degrees measured from the normal. What's the light ray going to do? It has to bend away from the normal. That side speeds up first. That stays slow until it comes out, bending away from the normal. This is the angle on the fast side. It's on top. We plug in 3.1 degrees, and we get 4.7 degrees. Okay, it's really an exaggerated diagram, but you get the idea. Let's see if it really works this way. Yeah, I guess so, huh? Let's finish with a medical application of total internal reflection. This is a solid glass, but very thin fiber optic cable. If we shine light through it at this end, it's just going to go straight through. But look at the angle that it strikes the surface. It's beyond the critical angle. Beyond the critical angle again. But when it gets to the end, it hits the terminus and escapes. So how can this be used in medicine? Hey, it could be a proctoscope, an endoscope, arthroscopic surgery. You take a thin fiber optic and you can stick it anywhere in the body and it'll illuminate a cavity. So let's say you're having a colonoscopy and this goes into your intestines. It can shine light inside there and the doctor can look for polyps. The light shines inside the intestines and comes back through a parallel cable into the eye. So we can now see what's going on in there. If you had a bleeding ulcer here, you could even attach a laser powerful enough to shine down through here and cauterize the laser without having to do surgery and go inside the body. So this is an example of fiber optics, all due to total internal reflection.